Chemistry provides the rule book for how everything in the universe interacts, combines, and changes. Matter is anything that has mass and takes up space. To understand how basic elements build the complexity of the world around us, we must first master the laws of chemical combination. The first of these is the law of conservation of mass. In a classic experiment using an H-shaped Landolt tube, a chemist mixes silver nitrate and sodium chloride. A chemical reaction occurs, forming a new solid, but the weight of the sealed tube remains perfectly balanced. Matter remains constant throughout the change. The law of definite proportion holds that a pure chemical compound always contains its elements in the exact same ratio by mass. This pie chart shows pure water. Whether you pull it from a lake or synthesize it in a lab, it maintains a fixed 1:8 ratio by weight of hydrogen to oxygen. When the same elements form different compounds, we look to the law of multiple proportions. Here, 12 grams of carbon reacting with 16 grams of oxygen forms carbon monoxide. On the right, 12 grams of carbon reacts with 32 grams of oxygen to form carbon dioxide. Look at the oxygen values. While the mass of carbon remains fixed at 12 grams, the differing masses of oxygen, 16 and 32 grams, bear a simple whole number ratio to each other. It simplifies to exactly 1:2. These specific weight ratios demonstrate that matter doesn't mix as a continuous paste. It combines in quantifiable, predictable blocks. In 1808, John Dalton formalized these observations into his atomic theory. He proposed that all matter consists of tiny, indestructible particles called atoms. Modern science later refined this into a modified Dalton's theory. Nuclear reactions revealed that the atom is not a solid sphere, but a complex arrangement of subatomic particles, protons, neutrons, and electrons. This structure explains isotopes. Because neutron counts can vary, atoms of the same element can have different atomic masses. These three variations of hydrogen possess atomic masses of 1, 2, and 3 atomic mass units. When these atoms bond into molecules, we can calculate their total weight. For sulfuric acid, H2SO4, we add the atomic masses of 2 hydrogens, 1 sulfur, and 4 oxygens to reach a molecular mass of 98 atomic mass units. Since a single molecule is too small to weigh on lab scales, we use the mole. By expressing that 98 in grams, we get the gram molecular mass. 98 grams of sulfuric acid equals 1 mole, containing 6.022 times 10 to the 23rd molecules. The mole lets us take theoretical atomic weights and weigh exact quantities on a physical scale. Most reactions happen in mixtures and solutions. On an industrial scale, it is critical to know exactly how much substance is dissolved in a liquid. We measure this using molarity, denoted by a capital M. To find it, divide the total moles of your dissolved solute by the volume of the solution in liters. Molality, denoted by a lowercase m, uses a different denominator. Here, we divide the moles of solute by the mass of the pure solvent in kilograms. For example, to find the molarity of 49 grams of sulfuric acid in a 1-liter solution, we first convert the mass to moles. Dividing 49 grams by the molecular mass of 98 gives us 0.5 moles. Dividing that by 1 liter results in a 0.5 molar solution. We can now see the progression from the foundational laws of chemical combination to the structure of the atom, the transition into the mole, and finally the practical application of concentration formulas. You can pause here to take a screenshot of this summary for your study notes. Mastering these laws and formulas provides the framework required to accurately predict and measure how the physical world behaves.